3:15 in the morning. The Anaconda Copper Works, third-floor conveyor hall. The air smells of wet brick and cold iron. Everything is still. The main drive shaft sits motionless in its bearings. The leather belts hang slack from the overhead line. The boiler fires were banked 4 hours ago. Steam pressure dropped to nothing by midnight, but somewhere in the darkness, metal groans against wood. The number 3 conveyor, 60 feet of oak rollers and iron brackets, begins to move. Not a jerk, not a slip. A slow, deliberate creep forward. 1 inch, 2 inches. The wooden rollers turn in their housings with a sound like bones shifting in sleep. No one is here to see it, just the drip of condensation, the tick of cooling metal, and that impossible motion, patient as a clock, continuing through the empty hours before dawn. Water runs down the brick walls in thin streams, collecting in the iron gutter along the baseboard. The windows are opaque with grime and frost. Outside, the Montana night is black and cold. Inside, the darkness smells of machine oil and wet copper dust. The conveyor moves another inch. The oak rollers are old-growth timber, dense and heavy, worn smooth by months of ore sliding across their surface. They turn in their bronze bushings with barely a whisper. Just that low wooden groan, like a ship's timber under load. Somewhere below, on the second floor, a steam pipe contracts with a sharp tick. Then another. The building cooling, settling into the night. But this motion, this is something else. This is deliberate, forward, continuous. By 4 o'clock, the conveyor has traveled 8 feet from its marked position. First shift comes through the doors at 5:30. Thomas Brennan leads 4 men up the iron stairwell, their boots ringing against the steps. They carry lunch pails and thermoses. Their breath clouds in the cold. Brennan stops at the threshold of the conveyor hall. The number 3 line has moved 12 feet from where they left it last night. The chalked position marks on the floor tell the story. The whole assembly has crept forward, silent, in the dark. Check the brake, Brennan says. Charlie Voss kneels beside the drum brake, puts his hand on the iron shoe. Set tight, hasn't budged. The men stand in a half circle, watching the conveyor, waiting for it to move again. The morning light comes grey through the windows, picking out the texture of the oak rollers, the rust on the frame bolts, the fine copper dust settled on every surface. Brennan walks the length of the conveyor, checking each section. The frame is 2-ton iron, bolted to oak stringers that run perpendicular to the floor joists. The rollers themselves are 8 inches in diameter, turned from white oak and mounted in bronze bearings. There are 23 of them, spanning 60 feet from the feed hopper to the discharge chute. Everything looks normal. Everything is in place. Except the whole assembly has moved a dozen feet while no one was watching. And then they feel it, a faint vibration through the floorboards. Nothing you'd notice if you were moving. But standing still, you can sense it. A rhythm, deep and slow. The conveyor shifts forward another half inch. The rollers turn with a soft wooden groan, no steam, no belt drive, no hands on the machinery. Brennan feels the hairs rise on his forearms, not from fear, from the wrongness of it. Machines don't move on their own. They obey force and friction. They obey men. Voss stands up slowly. Tom, you feel that? Yeah, through the floor, like a pulse. Other men are feeling it too now. Standing very still, boots flat on the pine planks, sensing that deep rhythm coming up through the timber. It's not constant. It comes in waves. Every minute or so, a gentle surge of vibration that makes the copper dust shift on the windowsills. Get Sullivan, Brennan says quietly. Tell him we've got a problem on 3.
By 7 o'clock, a dozen men have gathered in the conveyor hall. They don't speak much. They watch. The movement has become rhythmic now. Every 2 or 3 minutes, the conveyor creeps forward, sometimes an inch, sometimes less, but consistent, like breathing. Frank Morrison puts his hand flat on the iron frame. He's worked mills for 20 years, knows the feel of machinery the way a doctor knows a pulse. It's not slipping, he says. It's being pulled, but nothing is pulling it. The belt drive hangs dead. The main shaft is cold and still. The reduction gears sit locked in their housings. The men have checked everything twice. The drive drum is disengaged. The tension pulleys are slack. The clutch mechanism sits open, the jaws separated by a full inch of daylight. There is no mechanical connection between this conveyor and any source of power, yet it moves. Dust begins to shift on the horizontal surfaces. Fine patterns appear in the copper residue on the crossbeams, ripples like sand on a drumhead. The men watch the dust move in waves, responding to something they cannot hear. Morrison notices it first on the window ledge. The copper dust there has arranged itself in parallel lines like iron filings near a magnet, but these lines pulse. Every minute or so they blur and reform, slightly shifted. "You seeing this?" he asks. Brennan joins him at the window. Watches the dust patterns shift and settle, shift and settle. "What the hell is doing that?" "Vibration," Morrison says. "But I don't know from where." Then the sound starts, not loud. A deep hum felt more than heard. It comes up through the floor, through the boot soles, into the bones. The frequency is so low it makes the chest cavity resonate. Some of the men step back instinctively. The hanging oil lamps begin to sway, just slightly. All in the same rhythm. Peter Kasich, 19 years old, newest man on the crew, points to the far end of the hall. "Look at the number 5 line." The number 5 conveyor, 30 feet away and completely separate from number 3, is vibrating in its mounts. The oak rollers chattering against their brackets. No motion forward or back, just a steady tremor like the machine is afraid. The men move toward it slowly. Stand around the number 5 frame, hands hovering over the iron, not quite touching. "It's resonating," Morrison says, "like a tuning fork." Brennan puts his palm flat on the frame. The vibration travels up his arm into his shoulder. It's not random, it's rhythmic, precise. Like the building itself has a heartbeat. "Christ," someone whispers. The sound grows deeper, that subsonic hum rising from somewhere beneath them. The oil lamps swing in wider arcs now. Shadows dance across the brick walls, and in the midst of it all, the number 3 conveyor takes another patient step forward. Morrison turns to Brennan. His face has gone pale. "You ever see anything like this?" Brennan shakes his head slowly. "No, not once." By mid-morning, Patrick Sullivan has arrived, the mill foreman, a man built like a boiler with a face to match. He doesn't like mysteries. He likes problems he can hit with a wrench. He stands in the conveyor hall for a long minute just watching, arms crossed, face unreadable. Then he gets to work. He starts at the drive end. Kneels in the grease and copper dust, running his hands over every coupling, every bearing, every brake shoe. His fingers are thick and scarred from 30 years of mill work, but they move with surgical precision over the machinery. Checking the flywheel, checking the clutch assembly. Everything is disengaged, everything is cold. "Run me through it," Sullivan says. Brennan walks him along the conveyor length. Belts are slack, drive shaft is free, no air pressure in the brake system, no steam in any of the lines, but she's moving. Been moving since before dawn. Sullivan puts his weight against the frame, tries to rock it. The conveyor is solid, 2 tons of oak and iron bolted to the floor. You'd need a team of men and pry bars to shift it an inch, but it's been moving all morning on its own. Sullivan checks the floor bolts. They're tight. He checks the frame alignment with a machinist's level. Perfect. He checks the rollers for ice or debris that might be melting and causing a slide. Nothing. He pulls a roller pin, examines the bronze bushing underneath. The bearing surface is clean, properly oiled. No scoring, no excessive wear. He slides the roller back into place. "When's the last time this line ran?" Sullivan asks. "Yesterday afternoon," Brennan says. "Shut down at 4:30, cleaned and locked out by 5. Temperature in here last night? Below freezing, same as outside." Sullivan nods slowly, thinking. He walks to the discharge end of the conveyor where it feeds into the sorting chute, kneels there. Runs his hand along the gap between the roller assembly and the chute wall. There's a scrape mark in the paint. Fresh. "When did we install this line?" Sullivan asks. "Last April," Brennan says. 6 months ago." Sullivan runs his thumb along the scrape mark. "The wood is bright and clean underneath. This is new wear, recent. The conveyor has been rubbing against the chute wall as it moved." He stands and looks down the length of the hall. The morning light has strengthened now, slanting through the high windows and dusty columns. You can see the architecture of the building more clearly, the brick columns rising to the timber ceiling. The iron trusses overhead painted black. The way the floor beams span the full width of the structure, 60 feet of yellow pine timber supported at the ends but free to flex in the middle. Sullivan feels that vibration again through his boots, that deep, slow pulse. He closes his eyes, concentrating, trying to time it. 40 seconds between pulses, maybe 45. "Something's moving," he says. "But it's not the conveyor." Morrison frowns. "What do you mean?" "I mean the conveyor is just responding to something else. Something bigger. Sullivan opens his eyes, looks at the floor beneath his feet. This whole building is moving. That afternoon, the phenomenon intensifies. The conveyor motion becomes more pronounced, sometimes moving 2 or 3 inches in a single shift. The wooden rollers are warm to the touch from friction. The men stand back and watch it happen, helpless. But it's the other signs that disturb them more. The deep pulse through the floor has grown stronger. You can time it now. Roughly every 40 seconds, a wave of vibration runs through the building. It comes from somewhere beneath them, or maybe from far away. Hard to tell. During one of these pulses, Morrison holds up a lantern. The flame flickers and bends, all the lamps in the hall moving in unison, as if a draft is passing through. But the windows are closed, the doors are shut. Air pressure, Morrison says. Something's changing the air pressure in here. Sullivan watches the lamp flames dance, all in perfect synchronization. That shouldn't be possible with still air and closed doors. One of the men, a machinist named Otto Weiss, kneels and puts his ear to the floor. Listens for a long moment. I hear it, he says, like machinery but far off through the ground. They all try it, one by one, kneeling on the cold planks, pressing their ears to the wood, and they all hear it. A distant, rhythmic pounding, almost subsonic. The kind of sound you feel in your teeth. Boom, 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 regular as a metronome, coming up through the timber, through the foundation, from somewhere deep below. Sullivan stays down the longest, ear pressed flat to the floor, eyes closed, counting the impacts, timing them against his pocket watch. When he stands, his expression is grim. 42 per minute, he says. Whatever's making that sound runs at 42 strokes per minute. The stamping presses, Morrison says quietly. Everyone turns to look at him. Down in Building 6, Morrison continues. The ore presses, they run at that speed. Sullivan shakes his head. Building 6 is 300 feet from here. Separate foundation, no connection. Then where's the vibration coming from? No one has an answer. Sullivan walks to one of the iron columns that supports the roof trusses, puts his hand flat against the brick, feels the pulse travel through the masonry. It's definitely there. A rhythmic flex in the structure itself. He comes back with a plumb line, an iron weight on 20 feet of string. He hangs it from one of the overhead beams and watches it sway. At first it seems random, but over the course of 5 minutes a pattern emerges. The weight swings in a slow ellipse, tracing the same path over and over. The building is moving, not much, maybe a fraction of an inch, but moving. This isn't the conveyor, Sullivan says quietly. This is the whole damn structure. He turns to Brennan. I want every mechanical connection in this building checked. Every belt, every shaft, every coupling. I want to know if anything down below is running that we don't know about. Brennan nods. I'll get the crew on it and send someone to Building 6. Find out if the stamping presses have been running overnight. But even as he gives the orders, Sullivan knows something doesn't add up. The stamping presses are massive, steam hammers that crush ore into powder, but they're not connected to this building. Can't be. The foundations are separate. The structures are isolated, so why can he hear them through the floor? By the next morning, the mill superintendent has brought in outside help. 2 engineers from the Montana School of Mines arrive with instruments, transits, levels, micrometers, and surveying equipment. Their names are Aldrich and Pemberton. Both men in their 30s, wearing wool suits and carrying leather satchels. They set up in the conveyor hall like surgeons preparing for an operation. The mill workers watch with mixed feelings. There's resentment, college men coming in to explain what's wrong with machinery the workers know by touch and sound. But there's also hope. Maybe these engineers will see something they've missed. Aldrich runs a chalk line down the center of the floor, marking reference points every 10 feet. He'll measure movement against these marks over the course of the day. Pemberton sets up a theodolite, a precision angle measuring instrument mounted on a tripod. He sights along the length of the building, making fine adjustments to the leveling screws. He's checking for deflection in the floor beams, checking whether the structure is sagging or twisting. Sullivan stands beside them, arms crossed. What are you looking for? Structural deformation, Aldrich says without looking up from his notebook. If the floor is flexing, we'll see it in the measurements. And if it is flexing, then we need to know why and how much. By mid-morning, they've established a baseline. The engineers work methodically, taking readings every 15 minutes, recording angles, distances, variations. The mill workers drift back to their other duties, but a few remain, watching, waiting. The conveyor continues its patient creep forward. The engineers measure its progress with precision calipers. 1.3 inches per hour averaged over 6 hours of observation. At noon, Aldrich calls Sullivan over. "The floor is moving," he announces. Approximately 1/16 of an inch peak to peak, oscillating at roughly 1 cycle per 43 seconds, Sullivan nods slowly. So the conveyor is riding the floor motion. Exactly. The vibration is breaking static friction in the roller bearings. When the floor tilts even slightly, gravity pulls the conveyor forward. Small increments but continuous. What's causing the floor to move? Unknown. But it's not originating here. This is a secondary motion, a response to something else. Pemberton looks up from his theodolite. The building is acting like a resonator. Something is exciting a natural frequency in the floor beams. They're flexing in rhythm with an external force. Morrison speaks up from the back. "The stamping presses, we can hear them through the floor." Pemberton frowns. "How far away are those presses?" 300 feet, different building entirely. "That shouldn't be possible, not through separate foundations." "And yet," Sullivan says, "we can hear them, clear as day." The engineers exchange glances. This doesn't fit their understanding of structural isolation. Buildings are designed to be independent. Vibrations shouldn't travel from one foundation to another across that distance. Aldrich makes a note in his book. "We need to examine the foundations, see if there's any connection we're not aware of." That afternoon, they go down to the basement. The mill workers lead them through the boiler room, past the coal bins, into the foundation space beneath the conveyor hall. It's dark down here, cold. The foundation walls are stone, great blocks of Montana granite mortared together. The floor beams rest on iron pilasters set into the stone. Everything looks solid, permanent, but when they stand very still, they can feel it. That rhythmic pulse, stronger down here, coming up through the stone itself. Pemberton puts his hand on the foundation wall, feels the vibration travel through his palm. "It's transmitting through the bedrock," he says quietly. Somehow the vibration is traveling underground, from Building 6 to here. "How?" Sullivan asks. Pemberton shakes his head. "I don't know, it shouldn't be possible, not at this distance." They stand in the darkness, feeling the pulse of the stamping presses 300 feet away, traveling through stone and earth to shake the foundations of a building that was supposed to be isolated. Aldrich writes in his notebook by lantern light. His hand is shaking slightly. It would be another 30 years before anyone fully understood what happened in the Anaconda Copper Works that November. The explanation came in 1927, from a doctoral thesis written by a structural engineer named Howard Finch. He'd been studying industrial building failures and came across the old incident reports from Anaconda. The case fascinated him. He spent 2 years reconstructing the mill's layout, analyzing the foundation design, and interviewing surviving workers. What Finch discovered was this: the number 3 conveyor sat on the 3rd floor of the mill, directly above the main stamping press building. The presses, massive steam-powered hammers that crushed ore, operated on a foundation sunk 30 feet into bedrock. When they ran, they sent shockwaves through the ground. Normally, this wasn't a problem. The mill was built on separate footings. The foundation plans showed clear isolation between the structures: sand-filled trenches, expansion joints. All the engineering practice of the 1890s said these buildings shouldn't interact. But in October of 1897, a maintenance crew had dug a drainage trench between the 2 buildings. They were trying to redirect groundwater that had been pooling near the mill basement. They dug down 6 feet, following the foundation line. What they didn't realize was that they'd cut through a layer of hardpan clay that had been acting as a vibration barrier. Below that clay was solid bedrock, the same bedrock both buildings were founded on. For the first time, there was a direct path for vibration to travel from the stamping press foundation to the mill foundation. And the vibration did travel. Through granite, through limestone, through the deep bones of the Montana earth. But that alone wouldn't have caused the phenomenon. Vibration travels through rock all the time. Buildings shake. Machinery trembles. That's normal. What made this case special was the frequency. The stamping presses ran at 42 cycles per minute. 42 impacts, evenly spaced. That translated to one impact every 1.43 seconds. Each impact sent a pulse through the bedrock. A compression wave traveling at the speed of sound through granite, roughly 12,000 feet per second. Those pulses reached the mill foundation and traveled up through the stone walls, into the iron pilasters, into the timber floor beams. Now, here's where it gets interesting. The mill floor beams were 60-foot spans of yellow pine. Old-growth timber, dense and strong. But any beam that long has a natural resonant frequency, a speed at which it wants to vibrate. It's determined by the beam's length, mass, and stiffness. For these particular beams, loaded with the weight of conveyor machinery and copper ore, that natural frequency was very low. Approximately one cycle per 43 seconds. You see where this is going. The stamping presses hit 42 times per minute. That's one impact every 1.43 seconds. But the floor beams wanted to oscillate at one cycle per 43 seconds. The numbers don't match exactly, but they're close enough. Close enough for something called harmonic coupling. When a periodic force like the stamping press impacts is applied to a structure with its own resonant frequency, the structure can begin to vibrate at that natural frequency, even if the driving force isn't perfectly synchronized. It's like pushing someone on a swing. You don't have to push at exactly the right moment every time. As long as you're close, the swing will build up amplitude. The floor beams were the swing. The stamping presses were the push. Over the course of hours, the beams began to flex in a slow, deep oscillation. One cycle every 43 seconds. The motion was tiny, a 1/16 of an inch at most, but it was real. When the beams flexed upward, the far end of the conveyor would rise slightly. When they flexed downward, it would fall. The motion created a very slight, constantly changing incline. Now add in the friction dynamics. The conveyor rollers sat in bronze bushings. Under normal conditions, static friction kept them locked in place. You'd need dozens of pounds of force to overcome that friction and make a 2-ton conveyor move. But the vibration changed everything. The deep pulse from the floor, that subsonic rhythm, created what's called stick-slip motion in the bearings. For brief moments, the vibration would reduce the effective friction to nearly zero. During those moments, even the tiny incline from the beam flex was enough to let gravity pull the conveyor forward, one click at a time, one increment per cycle. The conveyor was walking forward, riding the slow breathing of the floor beams beneath it. But there was more. There's always more with these old structures. The mill had been retrofitted with a new ventilation system that summer. Large fans in the basement, designed to pull fresh air through the building and exhaust it through roof vents. The system used brick shafts, essentially chimneys, that ran vertically through the structure. When the floor beams flexed, they put stress on those brick shafts. Just slight compression and extension over and over. This caused microcracks in the mortar joints. Nothing dangerous, nothing you'd even notice. But those cracks changed the air pressure in the shafts. When the floor flexed down, the brick shafts compressed slightly and air pressure increased. When the floor flexed up, the pressure decreased. The result was a slow, rhythmic pulse of air pressure throughout the building. That's what made the lantern flames flicker. That's what the men felt in their chests, that deep, subsonic pressure wave cycling every 43 seconds. And finally, there was thermal contraction. November nights in Montana drop well below freezing. The iron frame of the conveyor, 2 tons of cast iron, would contract as it cooled. Not much. Maybe a few thousandths of an inch. But that was enough. As the iron contracted, it pulled against the bronze bushings. This added stress to the bearings, making them more susceptible to that stick-slip motion. The cold made the conveyor more willing to move. So you had 3 mechanisms working together. 1. Harmonic coupling through the foundation, transmitted from the stamping presses through bedrock to the mill floor beams. 2. Thermal cycling of the iron frame, increasing susceptibility to motion during the cold night hours. 3. Frictional oscillation triggered by structural resonance, breaking static friction at regular intervals. None of these forces was large. Each one by itself would have been insignificant, but combined, synchronized by the deep pulse of the stamping presses, they were enough to move 2 tons of oak and iron across 60 feet of floor. The conveyor wasn't being driven by any single force. It was being moved by the building itself, responding to rhythms transmitted through stone and timber from a machine 300 feet away. The men at Anaconda never learned the full explanation. The engineers of 1897 didn't have the tools to see it. Structural dynamics was still in its infancy. The mathematics of resonance and harmonic coupling wouldn't be fully developed for another generation. What they did know was this: they dug up the drainage trench and filled it with sand and gravel, a vibration break. Within a week, the movement stopped. The conveyor sat still. The deep pulse faded away. The mill ran for another 40 years after that. The incident was noted in the maintenance logs but never fully explained. Most of the workers who witnessed it are gone now. Their testimony survives in archived reports, handwritten in careful script. Conveyor moved without power, cause unknown, corrected by trench remediation. But the phenomenon they witnessed wasn't unique to Anaconda. Industrial-age structures, the great mills and factories and refineries of the late 1800s, were enormous machines in themselves. Thousands of tons of timber and brick and iron, all connected, all resonating. Buildings that breathed with the rhythm of their machinery. Structures that hummed and flexed and transmitted forces across distances their builders never imagined. There are other cases in the historical record. Not many, but they're there if you look. A textile mill in Lowell, Massachusetts, where looms on the fourth floor would start and stop in unison, even when their belts were disconnected. The building was vibrating at its resonant frequency, excited by water wheel impacts transmitted through the foundation. A grain elevator in Minneapolis, where wheat would flow upward through a stationary auger during certain hours of the night. The vibration from a nearby rail yard was creating standing waves in the grain itself. A steel foundry in Pittsburgh where molten metal in a ladle would ripple in perfect circles, even when the ladle sat motionless. The floor beneath it was pulsing with the rhythm of trip hammers 3 buildings away. The men who worked in these places rarely understood what they were seeing. They just knew that sometimes the buildings did things that machines shouldn't do, that the boundary between structure and machine was not as clear as the architects had drawn it. They lived inside instruments, buildings tuned to frequencies they couldn't hear, playing songs they could only feel through the soles of their boots. Thomas Brennan worked at the Anaconda Mill for another 30 years. He retired in 1927, the same year Howard Finch published his thesis. Someone sent Brennan a copy of the paper. He read it in his kitchen, by lamplight, moving his finger under the technical language, trying to understand. Later, someone asked him if it made sense, if Finch's explanation matched what he'd seen that November morning. Brennan thought for a long time before answering. "I suppose it does," he finally said, "though it seems awfully complicated for something that looked so simple." And that's the truth of it. The conveyor's motion looked simple, steady, almost peaceful. You could watch it creep forward and think nothing of it, just a machine sliding across a floor. But underneath that simple motion was a symphony of forces, vibrations traveling through bedrock, floor beams oscillating in deep harmonics, air pressure pulsing through brick shafts, metal contracting in the Montana cold, friction breaking and reforming 43 times an hour. All of it invisible, all of it connected. The stamping presses played, the building sang, and in that song on a cold November morning in 1897, a conveyor began to move. The men watched it happen. They felt it in their bones, that deep pulse coming up through the floor, that subsonic rhythm that made their chests resonate. And though they couldn't name the forces at work, they knew they stood inside something larger than themselves, something that moved to rules they hadn't written. Patrick Sullivan wrote in his final report, "Phenomenon ceased upon remediation of drainage trench. Recommend no further excavation between buildings 3 and 6. Recommend monitoring of all long-span floor structures for signs of resonant motion. Simple words, practical advice, but underneath them an unspoken acknowledgement. We don't fully understand what happened here. We've stopped it, but we haven't explained it. The building spoke to us in a language we don't quite know how to read. That was the real mystery, not that the conveyor moved, but that it moved in time with something they couldn't see, a pulse from the earth, a rhythm older than steam, a connection through stone that no blueprint had ever drawn. The mill is gone now, torn down in the 1950s. The stamping presses went to scrap. The yellow pine floor beams were sold for salvage lumber. The foundations are still there beneath new construction, but the buildings that stood on them, those great resonating structures that breathed and pulsed and sang, those are lost to time. Only the reports remain. And the story, the memory of men standing in a cold hall, watching a machine move without power, feeling the floor pulse beneath their feet, knowing they were witnessing something strange and profound, and just beyond the edge of understanding. They were right. They stood inside an instrument that played notes too low for human hearing. They worked in a building that danced to the rhythm of stamping presses 300 feet away. They witnessed the moment when architecture and machinery and earth all aligned in perfect, terrible harmony. And for 3 days in November 1897, they watched a conveyor walk across the floor, one patient step at a time, moved by the breathing of the building around it. That was the mystery. And it was beautiful.